Good morning, friends. This is Naga S. Ramat. I'm working as assistant professor in the Department of Electronics and Communication Engineering. So this is regarding embedded system. So in the previous part, that is part 1, we discussed what is embedded system, what are the examples of embedded system, and also we discussed the comparison between general purpose computing system with embedded system. In this part 2, we are going to discuss the main objectives, that is classification of embedded system, then elements of an embedded system, the core of the embedded system. First, we'll move on to the classification of embedded system. Mainly, we have two classifications of embedded system, the on generation and on complexity and performance level. On generation, we have mainly four types. In that, first one is first generation embedded device. In this first generation embedded device, these are 8-bit microprocessor or 8-bit microcontroller. So in this first generation embedded device, these devices are operating for the 8-bit of data. So only in each cycle it performs only 8-bit of data, and also microcontroller is also 8-bit of operation. For suppose if you consider the addition operation, if you want to add the value of 6 and 8, so to add these two numbers, we have to use the instruction. In case of microprocessor and microcontroller, we'll use instruction add. So these instructions performing only 8-bit of data, that is the value of 6 and value of 8 will be added and it will give the result. That performing operation is of 8-bit of operation. That is the meaning of 8-bit microprocessor and microcontroller. First generations are simple in hardware circuit and firmware developed. So whatever hardware and firmware is used in the first generation are simple. And examples for the first generation, that is digital telephone keypad. So this digital telephone keypad is of first generation embedded device. The firmware is also simple and hardware is also simple. The second generation, in this second generation, the processor is of 16-bit microprocessor and controller is of 8-bit microcontroller. So here, these instructions, whatever instructions available in the 16-bit microprocessor, those instructions performing 16-bit of data at a time, compared to the first generation, in that case 8-bit of data. Suppose you have 16-bit of data, in case of first generation we have to go for 2 cycles, but in case of second generation, in single cycle the 16-bit of data will be performed. That is the main difference between 8-bit and 16-bit processor. Then these second generation are more complex and more powerful than the first generation microprocessor and microcontroller. The reason is these are of 16-bit microprocessor. The performance level is increases compared to the first generation. That is the reason these are more powerful than the first generation microprocessor. If you observe the complexity level compared to the first generation to the second generation, the complexity level is increases because we are operating for the higher operations. That is the reason the complexity level is increases from the first generation to second generation. The example is SCADA system. So this is the SCADA system diagram. So here how the data will be controlled from the main server part to the individual devices. Then third generation embedded system, these are of 32-bit microprocessor and 16-bit microcontroller. See here the number of bit of operation is increases from the 8-bit to 16-bit. Then now third generation of 32-bit microprocessor, and the microcontroller is of 16-bit of data. So it performs 16-bit of data in a single clock cycle. That is the meaning of 16-bit microcontroller. Then concepts like the digital signal processor, application specific integrated circuits are included in the third generation embedded devices. The examples, the robotics, media. So these are all belongs to third generation embedded devices. In the fourth generation, these fourth generation devices are made up of 16-bit microprocessor, 32-bit microcontroller. The concepts of SoC, multi-core processors are included in the fourth generation embedded devices. These are complexity level is more in case of fourth generation, but the performance level are powerful compared to the other generation, first, second, third generation. If you compare, the more powerful than the earlier generation devices. The examples is for the fourth generation is smartphone. Then so these classification are based on the generation, first generation, second generation, third generation and fourth generation. And another type is on based on the complexity and performance level. Based on complexity and performance level, we have three types. The first one is called as small scale embedded system. So as the name indicates, so these embedded devices are used for the smaller applications. So those are simple in application and performance is also the very lower level. So we can't expect high performance for the small scale embedded devices because of the operating speed. You can observe here the 8-bit of data or 16-bit microprocessor will be used in these small scale embedded system applications. So that is the reason these devices are used for the smaller applications. 8-bit or 16-bit microprocessor are used, or microcontroller are used in these devices. The examples: an electronic toy. Medium scale embedded system, the slightly complex in hardware and firmware requirement. See, compared to the small scale, the complexity slightly is increases and firmware, that is programming requirement, is also increases because of the application level is increased. Then built around medium performance, the performance level is also increases, and these are of low cost. 16-bit or 32-bit microprocessor are used in the medium scale embedded system devices. Then usually contain the operating system, the OS is present in the medium scale embedded system. Next, examples: industrial machines. The third one, the large scale embedded system. As the name indicates, these embedded devices are used for the larger application. So what happens, the bit of data will be performed in this embedded device will be more compared to the small scale and medium scale. In the small scale and medium scale, we have 8-bit or 16-bit of processor, but in the large scale embedded system, it may be 32-bit or 64-bit of microprocessor will be used in the large scale embedded system. But the complexity level is increases in this larger scale embedded device, and the firmware is also requirement will be more. So this is of classification of embedded system. The next topic is on elements of an embedded system. What are the elements will be present in the embedded system? As we know, it mainly includes three parts, that is hardware, software and also the mechanical components. So this is an elements of an embedded system diagram. So here you can observe the input devices, output devices, those are connected through the ports, input ports and output ports. The input devices are used to provide the data from the input device to the main core of the embedded system. The output devices are used to display the output result. Then in the system core, that is the main chip, in that we'll use the different processors. So that we'll discuss in the next topic, that is main embedded system core. Then memory unit, that is whatever the operation is carried out, that will be saved in the memory unit. We have different types of memory, primary memory and secondary memory, like RAM, ROM, PROM, EPROM, flash memory. Okay, and other devices will be communicated through the communication interfaces like USB, parallel interface. Through that we can communicate output devices that will be connected to the system core by using communication interface. The core of the embedded system. So core of the embedded system mainly includes the general purpose and domain specific processors. Under that we have mainly three. The first one is called as microprocessor. As we know, the microprocessor, it takes the data, perform the operations and it gives the output. There is no control over the operation. But in case of microcontroller, it performs the operations and also it has a control over the operation. That is the main differences between microprocessor and microcontroller. Then another one is the digital signal processor, DSP processor. If you use DSP processor, the speed of the performance level will be increases. So these are the three main general purpose and domain specific processors are used in the core of the embedded system. Apart from this, we have the programmable logic device, The PLDs, under PLD, we have mainly two PAL, programmable array logic, and programmable logic array. These programmable logic devices that helps to the user to design their own constraints. So that is the advantage of PLDs in the embedded system. Then application specific integrated circuits. With respect to the applications, we can design the code that will be implemented in the ICs, application specific integrated circuits. Then commercial of the self components. We'll see one by one these processors. The first we'll move on to the microprocessor and microcontroller. If you see the general block of microprocessor, it mainly consists of control unit, then ALU and the registers and also CPU. These are the main block present in the microprocessor: register unit, CPU, the ALU and also the control unit. It just takes the data, process it, and it gives the output. So but in case of microcontroller, along with these components, we have the extra units, that is counters is available, timers and memory units like RAM, ROM. These are all inbuilt in case of microcontroller. But in case of microprocessor, if you require counters, timers, memory unit, you have to connect externally to the microprocessor. If you observe some differences between microprocessor and microcontroller, the microprocessor are widely used in the computer system and microcontroller is widely used in the embedded system. It is used in the embedded system. And as we observed in the block, it has only CPU embedded into it. The CPU will be present in case of microprocessor. In case of microcontroller, along with CPU, we have the fixed amount of memory unit like RAM, ROM and other peripheral devices like counters, timers, interrupts that will be included in a single chip. That is the main advantage of microcontroller over the microprocessor. Compared to other differences, in case of microprocessor, we have to connect all the components externally, so the circuit becomes large and complex. So here if you performing some operations by using microprocessor, some extra units to be connected. If you connect the extra units to the microprocessor, the circuitry level complexity will be increases. But in case of microcontroller, if you use the microcontroller to perform the operations, so the required devices will be inbuilt. So what happens? The circuitry size will be less. That is the reason the complexity is reduced in case of microcontroller compared to the microprocessor. Then microprocessor consumes more power. The power requirement will be more. That is, it consumes more power. Processor will consumes more power, but controller consumes very less power compared to the microprocessor. Then the last difference, as it rely on external storage, it need high processing time. Nothing but in case of microprocessor, we are connecting the memory unit externally. The processing, we have to access the data from the memory, it takes the time. That is the reason the processing time will be high in case of microprocessor. But in case of microcontroller, nothing but the data we can fetch immediately from the memory unit that will be available inside the microcontroller. The processing time will be very less. So that is another advantage of microcontroller. So these are the few differences between microprocessor and microcontroller. Then DSP, the digital signal processor. So as I told you, digital signal processor, it is the powerful special purpose 8-bit or 16-bit or 32-bit microprocessor designed to meet the computational demands and power constraints of today's embedded audio, video and communication application. In these applications, we can observe the DSP. If we include the DSP in this embedded device, the speed, that is performance level of the embedded device will be high. So that is the main advantage of digital signal processor. Then DSP are 2 to 3 times faster than general purpose microprocessor in signal processing applications. Compared to the general microprocessor, if you included DSP, the speed of the processor will be more 2 to 3 times faster than the general purpose microprocessors. Examples: audio, video signal processing, telecommunication and multimedia applications. Then application specific integrated circuit. This is another processor we included in the embedded core. The ASICs, application specific integrated circuits, is a microchip designed to perform a specific and unique applications. It will be included to perform the specific operations, or we can say that unique application. In unique applications will include the ASIC processor. Because of using this single chip for integrates several functions thereby reduces the system development cost. If you include this application specific integrated circuits, we can reduce the cost level of the product. So that is the more advantage of application specific integrated circuit processor compared to the other processors. Programmable logic devices, PLDs. So the main advantage, as I told you, we can user can design the circuit for their own applications. PLD is an electronic component. It used to build digital circuits which are reconfigurable. The meaning of reconfigurable in the sense, as user wants, like that we can design the circuit and we can perform the particular operations. A logic gate has a fixed function. So in case of logic gates, we are performing only that particular task only. Okay, but if you use the PLD circuit, PLD does not have a defined function, nothing but fixed function at the time of manufacturer. So we can perform the different level of logic circuitry by using the PLD circuit. The advantage of PLDs offer customer much more flexibility during the design cycle. As we designing the circuit, so we can make the flexibility level of the circuitry with the help of PLDs. PLDs can be reprogrammed even after a piece of equipment is shipped to a customer. Nothing but it is a pre-programmable. If the user wants in the other different manner of the project, then user can change the circuitry level. We have the main two circuitry level in this PLDs, that is PAL, programmable array logic, and programmable logic array. So with the help of these concepts, we can reprogram for the circuitry. The major advantage of using COTS is that they are readily available in the market or cheap, and a developer can cut down his or her development time to a great extent. The major drawback of using COTS components in embedded design is that the manufacturer of the COTS component may withdraw the product or discontinue the production of the COTS at any time if rapid change in technology occurs. If the technology changes, so there is a changes in the circuitry level. In that cases, so the use of the COTS will be negligible. That is the reason normally we won't include the COTS components in the embedded devices. The advantage of COTS: ready to use, easy to integrate, and reduce the development time. If you like this, please share and subscribe. Thank you.